Hello and welcome to our presentation. My name is Xander Bush.
And my name is Louis Livingston.
And we're going to be doing our project on using artificial intelligence in order to prescribe medicines. So our introduction is going to touch on how personalized medicine is becoming a much more prevalent topic in the medical field. It is based around using machine learning in order to create. Well, it doesn't specifically use machine learning, but it allows for the usage of machine learning in order to filter and prescribe medicines based on symptoms and other prevalent factors. So on our left, we see in the figure personalized cancer therapy. We can see a visualization of how cancer treatments are chosen for patients based on their personal details, such as symptoms, genomic dispositions, and other factors that can have to do with drug response. And drug response is a very key feature that we have to take into account when we are dealing with the prescription of drugs, because the drug response can make or break how effective a medicine can be. So on the bottom right graphic, we see the cost per genome for the cost to examine, and we can see that it went drastically down in recent years, and that is thanks to machine learning techniques being used for the decoding of genomic information. This allows for higher throughput when we're examining this data, because it can be very, very complex and it's very difficult for people to understand. And so using machine learning, we're able to find patterns in that and hopefully map the specific mutations into dispositions towards certain diseases and cancers. This has to do with the genomic and pharmacogenomic fields, which are biology disciplines that have to do with the usage of genomes as well as their structure and variations as well. And the pharmacogenomic has to do with using that information to prescribe medicines. In our project, we used many different techniques for working with our data set that is shown in the bottom left slide. The bottom left section is going to be a link to our repository as well as the source code for the data sets. So in the top right of the techniques used section, we can see a visualization of how the word-to-vec pre-processing technique changes large amounts of text into neural network input by using a artificial neural network to pre-process those words and try to link word significance together in order to better understand the content contained in that text.
Correct.
And Louis is going to take over on the rest of the techniques and the gathered data.
Correct. So as we move on, we're going to discuss the structure of our personal artificial neural network. So the way we architected it was we started with an input layer, and then we moved it into an embedding layer. And that embedding layer is mostly where the word-to-vec processing is. After word-to-vec has executed, it processes all the words in the embedding layer. Then it moves into an LSTM layer as another hidden input layer, and then it finally moves into a dense layer as the output layer. From there, we'll discuss the gathered data, the summary and gathered data. So where we got our data from was a Kaggle competition from around 3 years ago, which was based around this kind of idea of personalizing medicine with using machine learning. And so they did a couple of different things which allowed them to try to examine the best way to do it. So the data that they had was from clinicians, and it was their handwritten notes, which was matched to a classification. And so what the process of word-to-vec was going to do was take those handwritten notes, convert them into vectors so that the artificial neural network could process them and match them to classifications. So as we move on to our results section, we can see where the baseline project from Kaggle, where they were at, which was at a loss function of about 1.444, and our improvements actually negatively impacted with our new model, which was at 7.222. But that was the best we could do to be able to try to raise the accuracy at any point. Anything else we try to do to lower the accuracy. So even marginally, at the sacrifice of raising the accuracy, we had to increase the loss function. But that unfortunately was a side effect of messing around with the LSTM layer to be able to try to get to this point. And then so we will move on to the future plans, and I'll let Sander discuss those.
So our future plans for this project, what we hope to be done towards this topic in the future is we hope that there's an improvement to the throughput, because as our new model illustrates, in order to increase the accuracy at any point, we have to take a massive loss to the loss function. This can hopefully be remedied with different techniques and different breakthroughs in the machine learning techniques, as well as possibly integration of the GPU processing, because the GPU is a lot more suited towards the linear algebra-based calculations that neural networks have to perform. We can also, that would hopefully improve the accuracy, because accuracy at 45% for classifying patients based off their symptoms is not very good. Having a majority chance of being incorrect is not something that would be accepted in the medical field. So allowing for higher accuracy, faster processing, more accurate processing would help this project significantly, as well as possibly implementing more types of data sets that we can use in the project, as well as being able to use multiple data sets in one run with different inputs and being able to classify those compared to different information. Hopefully we'd be able to take somebody's genomic variations mapped into using a PyGeno, which is one of the libraries that we were experimenting with, and possibly using that as an input for our neural network, and seeing if we can classify that like how we could classify a patient based on their clinical research, on the clinical research done on them. Otherwise, this is a quick overview of our poster, and up to you, Lewis.
Thank you. So, correct. So that concludes our presentation for this. If there are any Q&A, or if there are any questions, we will be available during the Q&A portion of the C-Day and our emails are also at the top. If there's any questions outside of that, please feel free to email us. Thank you. Goodbye.
Thank you.